Now let's talk about the vector addition. If we are going to consider the vector A and the vector B, so in here we have this vector A and we have this vector B here. So vector A is equal to AXI plus AYJ plus AZK for its rectangular representation, and for vector B we have the BXI plus BYJ plus BZK for its rectangular representation. So if we are going to let C to be the sum of the vector A and B, so if this vector C here is the sum of the A and B, so we can say that the vector C is just vector A plus vector B. So for the vector A, this is the rectangular representation and the vector B is this. So this is just the sum of the components. So along the X, the Y, and the Z. Now, for this, what we are talking about here is just this vector C is just the resultant of the vector A and B. If we are going to sum up all of the forces, then the answer is just the resultant of all the forces. So if we are going to solve for this, now so for the X component, Cx, that is just equal to Ax plus Bx. And for the Y component of the resultant, C, that is just equal to Ay plus By. And for the Z component, that is just equal to Az plus Bz. So from here, we can say that the vector C is just equal to Ax plus Bx I plus Ay plus By j plus Az plus Bz k. We'll be having example for this when we go to our chapter 2 under the topic of the resultant of the forces. And we have here the vector subtraction. So the resultant of the difference between two vectors A and B of the same type may be expressed as R prime is equal to A minus B, wherein that is just equal to A plus the negative of the B. So this vector sum is shown graphically. Subtraction is therefore defined as a special case of addition. So the rules of vector addition is also applied to vector subtraction. If we are going to illustrate this, if we have this vector A here, and we have here the vector B, so since we are going to subtract, so what we will be having here is this vector B will be negative B, so we are just going to change its direction in order for it to become negative. And using the parallelogram law, we just have this vector A directed in this direction, and we have the negative of B directed in this direction. So this is just this A plus the negative of B. And using the parallelogram law, if we are going to copy this A here, and this is the negative of B here, the diagonal is its resultant. So the resultant vector is this R prime. But if we are going to have a triangle construction, so from here we have the A, and we have here the negative of B, then we will just have the same value of this resultant r prime here. And for the vector multiplication, if a vector is multiplied by a positive scalar, its magnitude is increased by that amount. Multiplying a negative scalar will also change the directional sense of the vector. So let's say we have here the vector A, and if we are going to multiply that by 2, so we will be having the vector 2A. That is the same vector with the magnitude of double of that of A, the same direction. But if we are going to multiply this by negative 2, it will be twice its magnitude but opposite in direction. And if we are going to multiply this by the negative of A, then it is just this vector A, the same magnitude, opposite in direction. And if we are going to multiply this, let's say 0.5 of A, then it is just half of this vector A. If it is negative 0.5A, then this is just half of the vector A, but opposite in direction. What about the dot product? In the figure, it shows the vector A and B, wherein the theta is the angle between their positive direction. The dot product of A and B defined as A dot B, wherein the theta must be between 0 to 180 degrees. Because the dot product is a scalar, it is also called a scalar product. Note that the dot product is positive if it is less than 90 degrees, and it will be negative if it is greater than 90 degrees, and it will be 0 if that is equal to 90 degrees. So the properties of the dot product. First, the dot product is cumulative. When we say cumulative, so let's say we have here the vector A with, so this is how we are going to write the vector A using instead of a boldface, no? Kasi kung ini-encode natin, boldface ang gamit natin, pero kung handwritten or drawing, we are going to provide arrow dun sa taas. So the vector A has the rectangular representation of AXI plus AYJ plus AZK. And for the vector B, we have here the BXI plus the BYJ plus the BZK. Now, if we are going to have our dot product, we are just going to multiply this AX with the BX, this AY with the BY, and the AZ with the BZ. So it says here in property number 1, the dot product is that the dot product is cumulative. When we say cumulative, so let's say we have A dot B that is just equal to AX BXI plus AY BY J plus AZ BZ K. And if we will be having the B dot A, so it is just BX AXI plus BY AY J plus BZ EZK. Now, if we are going to rearrange this, and this, so ito pa rin yung makukuha natin. So, it says here that the dot product is cumulative. And it is also distributive. When we say distributive, we can So let's say we have this b plus c here, so we can just distribute that vector A to vector C here. So we will be having A dot B plus A dot C. So kung titingnan natin, dadagdag tayo ng isa dito. We have here CXI plus CYJ plus CZK. So ito muna. So we have here A dot B plus C. Sabi niya, this is just equal to A dot B plus A dot C. Kalagyan ko na ng arrow sa taas kasi handwritten yung gamit natin. Okay. So for this, for the vector A, we have AXI plus AYJ plus AZK dot the sum of the B and the C. So we have for the sum of B and C, that's X plus X. So we have here bx plus cxi plus by cyj plus bz czk. Then we are going to distribute this. For the ax, we will be distributing that here. And for the ay, so distribute natin yun siya dito kay j. And for the az ay i-distribute naman natin siya dito. So we will be having here ax bx plus ax cxi plus we have here ayby plus aycyj plus azbz plus azczk. Then we are going to check if this is just equal to a dot b plus a dot c. So let's see. So we have here a dot b. Just multiply this a with the b here. So we have ax bx I plus ay byj plus az bzk. Then for the a dot c, so we have ax cx I plus ay cyj plus az czk. Then if we are going to sum them up, so we have ax bx plus ax cx so we will be having here ax bx plus ax cx I, and for the j we have here ayby plus aycyj. So dito kay I, ito yung tinag natin. So yun. And for this j, itong dalawang to. And for the k, ito at ito. So we have plus az bz plus az czk. Now if we are going to compare this, no? So this is just equal to this, and this is just equal to this, and of course this is equal to this. So it says here that the dot product is distributed. This is our property number 2. But from the definition of the dot product, we have to note that the base vector of the rectangular coordinate system will be satisfying these identities. The dot product I dot I, the j dot j, and the k dot k is just equal to 1. And if we are going to have the product of I and j, the j and k, the k and l, that would be equal to 0. So as you can see here, we have for the dot product, no? So ginawa natin kanina ay we have here the I and the I, the J and the J, the K and the K. So, meaning dito, itong mga I, itong J, at itong K na to, ay idadrop na natin kapag magkakaroon tayo ng dot product because these I, the J, and the K is just equal to 1 according dito sa ating definition of the product. So, simplifying this, and we will just have the ax bx plus ay by plus az bz. And of course, the same with this, no? The same yan dito. And itong mga to, since 1 lang yan, ay ito pa rin yung magiging sagot natin. Ax bx plus ay by plus az bz. So, dito ay idadrop na rin natin yung igk. Saan ba natin ginagamit yung dot product? So, one of the application of the dot product is finding the angle between two vectors. So, the angle theta between the two vectors A and B here in the figure can be found from the definition of the dot product. We have the cosine of A dot B over AB. So, from the definition earlier, these bold-faced letters here are the vectors, while this italicized letters here are the magnitudes. No? So, we can say that the cosine of theta is just equal to A dot B over AB. So, itong A is the magnitude of the vector A, and this B is the magnitude of vector B. And this is just equal to the vector A over its magnitude dot B over its magnitude. So if we are going to let this A, vector A over its magnitude as the lambda A, and this B, vector B over its magnitude as the lambda B, as the unit vector that have the same direction as A and B, then we can say that the cosine of theta is just lambda A times lambda B. Another application of a dot product is to determine the orthogonal component of the vector in a given direction. So if we are going to project B onto A in the figure, this length here, B cosine theta, is the orthogonal component of the vector B in the direction of A. Because the theta is the angle between A and B, and from the definition of the dot product, so from the dot product, we have the A dot B, this is equal to AB cosine theta. Then we can say that the B cosine theta, ito yung hinahanap natin, wherein that's the orthogonal component, is just equal to the vector A dot vector B over A. No? So, ito ay naibaba lang siya dito. Therefore, we can say that we have here the vector B multiplied by the vector A over A. But this vector A over A here can be expressed also as the lambda A is the unit vector in the direction of A. Therefore, this B cosine theta is just B lambda A. So the orthogonal component of B in the direction of A is equal to the vector B times lambda A.